All right, so as you've been hearing about just now, and we'll hear all throughout the day, how Bitcoin is the first decentralized digital currency and how it's revolutionized the financial world. However, as more and more people use Bitcoin, the network needs to handle a growing number of transactions. This is where Bitcoin scaling comes in. Scaling means improving the network to handle more transactions per second, basically. The number I hear tossed around is the Bitcoin blockchain can handle about 7 transactions per second on the base layer, whereas the credit card agencies can do tens of thousands per second or maybe even more. So making Bitcoin accessible and efficient for millions and eventually billions of users will take solutions like that we're going to talk about today. Some of those include the Lightning Network, side chains, and maybe we'll even get into some advanced technologies like ZK proofs. So for this, we have a panel of 2 here. Our first panelist is Vikash Singh, principal investor at Stillmark, a Bitcoin-only venture capital firm. He's passionate about the Internet of Money. He focuses on identifying companies poised for breakout performance in Bitcoin and Lightning technology. And joining us is D++, a pioneering figure known for her ability to simplify complex technical topics and her work with PlebNet, a sort of a grassroots peer-to-peer Lightning network. She has also developed and led a graduate-level Bitcoin engineering course at UT Austin. They're both based in San Francisco, but were kind enough to come out here for this conference. So please give them a warm welcome.
Yeah, so great to be here. Really enjoying the conference thus far. So as Eric mentioned, I currently work as a VC focused in the Bitcoin ecosystem, but my background is as a software engineer and a deep learning researcher for the decade prior to that. So I spent time incubating moonshots inside of Google's Moonshot Factory, focused on the intersection of machine learning and quantum computing, and also machine learning and bioinformatics, and then spent some time in the health tech startup space. And have been passionate about Bitcoin since 2015. So when the opportunity came to contribute to this space full time, I dove in 2021. So I do a combination of investing and also technical research, some of which was actually released today. So if we have time, we can get into that on machine learning and Lightning pathfinding.
Hi, I'm D++. I'm a computer engineer turned Bitcoin educator. Been in Bitcoin since 2013. And my favorite thing to do is to create interactive, gamified learning experiences. So as a programmer, I'm able to make fun games we can play that help deepen our understanding of Bitcoin. I was known for creating PlebNet, which is a peer-to-peer learning environment for Lightning node runners. But I'm always getting asked to talk on these Lightning panels. I'm actually a lot stronger on the main chain, but no one ever asks me to talk about Bitcoin transactions. You know, I can parse transactions in hex. I can't do that in Lightning. I can write Lightning applications, but to me, I feel that I know very little about Lightning comparatively, but you know, here I am.
Once PlebNet, always PlebNet. Well, we did a little prep call last week about this, and it was really great hearing the 2 of them talk. D++ especially had a bunch of questions for Vikash, so maybe we can just start off with that. You want to?
Well, yeah, I was going to say, I don't know that I need a moderator because I feel like I have so many questions for Vikash. I just kind of want to pick.
That's great. I can just sit here and look pretty while you do the work. Thank you.
Well, I'm just here to learn. Like I said, I have so much to learn. So like one of the things that we kind of talked about that is something that is completely Greek to me is the concept of ZKP, zero knowledge proofs, and optimistic rollups. And for me as a Bitcoiner, you know, no offense, not having come from the shitcoin world, I don't know the first thing about that stuff. So I'm just here to learn.
Yeah, I think it might be helpful to maybe from first principles derive some of the scalability limits of the Bitcoin blockchain. And then we can look at the different scaling solutions that have developed over the years and kind of contextualize them and then look at trade-offs, right? So when people say Bitcoin blockchain can do, at 7 transactions per second, 5 to 10 transactions per second, really the reason that is you look at transactions per block and then blocks per unit time, right? And there's 2 variables, right, at a very fundamental level. If you increase the transactions per block, this is kind of well discussed in the block size war from many years ago, you increase the cost to validate a node, and that is a threat to the decentralization of the network. So there's a limit to which you can do that becomes a centralizing force. On the other hand, right, if you decrease the block time, right, it's well researched that actually destabilizes the consensus, and you'll have exponentially more forks of the Bitcoin blockchain. So fundamentally, we are at a crossroads here, or not a crossroads. We are at a situation where blockchains fundamentally do not scale to millions of transactions a second, right? And this was sort of studied from the start, and people started learning just more and more things. So just with that in mind, let's take a look at the solutions that have been developed, right? I'll break them into three families of solutions and kind of explain what each of them is. First, we'll talk about sidechains. So Blockstream released the Liquid sidechain paper. This is essentially another blockchain that is pegged to the Bitcoin blockchain. The access to go from Bitcoin main chain to the Liquid network is through a federated multi-sig. But again, just going back to the principles that we developed, this is still a blockchain. So when we talk about sidechains in terms of transactions a second, we're really talking about a scalar multiple on transactions per second that you get, when we're talking just about general scalability, right? So I'll contextualize this. Maybe this is one perspective. If what we're talking about is, bringing the velocity or scale of money to anything close to that of the internet, the kind of scale that we are talking about is billions per second, right? Like the HTTP calls, it's very difficult to actually track this data, but the scale of the internet is that billions of HTTP requests happen every single second, right? So that's kind of the scale that I want to start, contextualizing when we think of all of this. So moving along, sidechains have very interesting properties, themselves. Like you can have different opcodes that provide for different things. Confidential transactions are there on the Liquid network. You have some different transaction or different, introspection opcodes that exist on Liquid. So very interesting in and of itself, and we can even go into the intersection of Lightning and Liquid and all of that. Payment channels, Lightning network. So Taj Drija and Joseph Poon put out that paper initially. This concept is ultimately you lock your Bitcoin in a 2 of 2 multi-sig, and there's some magic that's able to happen where you can actually update who owns what in that split of 2 parties. You can actually technically extend it to a little more than 2 without hitting the main chain, right? So when we talk about the formulaic constraints that we derived initially, the Lightning Network has this unique property where you can have transactions between 2 parties, where each transaction does not occupy block space. This is unique in the sense that now, theoretically here, you have problems like liquidity that needs to be deployed. You have a lot of other challenges that are bootstrapping such a network. But here, I think of all the solutions that we will talk about, upper bound theoretical scalability, a payment channel network has its strengths. The last thing I'll get into, since it's a hot topic.
Just one quick thing. So this is where people use the bar tab analogy. Would that be right for a Lightning channel where you update your tab, but you're not necessarily making a payment?
Exactly. So the concept really is that you're able to update the balance between you and another party, right, without hitting the main chain. So that whole equation that we developed on, block space being the constraint, you in some ways are escaping that in Lightning, but not completely, because there is an on-chain footprint to open a channel and ultimately close the channel. So the last one in this family, which is a hot topic now, which you also were talking about or mentioned, is zero knowledge proof. So first I'll talk about zero knowledge proof a little bit, just independent of blockchains, and then I'll discuss its application to blockchains and how it's sort of developed. Ultimately, zero knowledge proofs fall under this category of verifiable computation. And what this essentially means is that you have some inputs to a function, so you have some variables. You have some computation that's run that changes the state of things, so just kind of a regular computer science function, right? And then you have an output, and this cryptography is actually able to verify that that input to output transition occurred without running the function itself. Actually, to me, it's pretty magical that that's a thing if you really zoom out and look at it. So what does this mean in the context of Bitcoin, right? What is the computation actually that is happening on the Bitcoin blockchain? The computation that's happening is the ownership of who owns what, ultimately reflected in the UTXO set, is changing, right? So this is the computation that the Bitcoin scripting language, which is a stack-based language, as you may or may not be familiar with the opcodes, that's what it does. So a zero-knowledge proof, when it comes to the blockchain, all that leads to solutions like a zero-knowledge rollup, right? And in this kind of construction, you send your UTXO into a rollup contract or a bridge, whatever people call it, and now you're in this alternate system, right, where computation or ownership changes on that rollup can happen without actually touching the Bitcoin blockchain. In that world, right? Then what needs to happen is after all those state changes happen on the rollups, right, there's a piece of software that can produce a zero-knowledge proof that these computations got executed and then submit it back to the Bitcoin blockchain. So that ultimately is how rollups work. There's a lot of confusion here, so I will say this about rollup scalability versus Lightning. What rollups do enable that is a little bit different than Bitcoin's script is that the zero-knowledge proof for this verifiable computation paradigm is advanced enough that it can actually verify any Turing-complete function, right? So all the expressivity limits that people talk about when it comes to scripts and people are talking about covenants, when you're in that rollup land, you can have EVM equivalents or Ethereum virtual machine equivalents, and you can basically, develop whatever expressive smart contracting you want in that land, right? So that's something new. Scalability perspective, however, as it currently stands, every transaction that occurs in a rollup gets compressed, it's in the proof, and then it gets submitted back to the Bitcoin blockchain, but it still occupies some space. So even if every Bitcoin block was full of rolled up transactions, you get 40x improvements. So it's not like Lightning in that upper bound scalability.
This is one of the more technical talks of the day.
So these are like these are the three solutions, and maybe just for the audience, I'll kind of just outline an example here, right? On maybe some practical applications, right? Let's just say we wanted to live in a world towards internet scalability of money, where every time you liked something in TikTok, every time you liked something in Instagram, every time you did a Google search, that corresponded to some programmatic micropayment happening, right? There's an argument to be made that right now, L1 blockchains will not get you there, or anything close. Rollups do not get you there, as outlined, because every single rollup transaction occupies some layer 1 block space, right? So Lightning kind of emerges as a very strong candidate here, even though there are weaknesses to the Lightning design as well. So I'll kind of contextualize that. There's this concept of L402, which is extending the HTTP set, basically, to make it so that a server can actually respond when a client hits it and say, well, you need to send me half a penny, and then I'm going to respond to you, right? So when I talk to developers, this actually, to them, seems like an extension of the internet, right? Because HTTP, without knowing Lightning, people know what HTTP is if they've done web development, right?
Yeah, and my understanding is that 402 error code is like from the very beginning of HTTP of like payment required. But there has been no internet native money where you could do this easily. How are you going to pay half a cent or something?
Yeah, exactly. And then when it comes to like why Lightning might be, a promising candidate for HTTP 402, we look at, again, scalability, right? We need, if this is going to be widely adopted, you cannot have a system where every single HTTP 402 call has some sort of print or some sort of footprint on the Bitcoin blockchain. So that's pretty clear. Instant settlement is pretty important, because for this to work, you need to instantly settle your transaction, and then the server has to be able to confirm cryptographically that it received what it said it received, and then give the response. So these are also interesting aspects for Lightning being a candidate for L402.
Cool. Well, I guess I'll jump in and maybe add a couple things, if that's okay. We talked about sidechains, which don't scale Bitcoin. And I'm so happy you said that. Ben the Carman, who's one of my favorite Bitcoin developers, has a pretty cool article that he posted on Stacker News that says blockchains don't scale, and Liquid really isn't kind of a scaling solution, because to your point, what you're getting is a scalar multiplier, or in other words, maybe a 2x or a 3x or a 4x. That doesn't get us to billions of people. We don't need to just scale by 2 or 3 or 4. We need to scale exponentially. So how do you do that? Well, Lightning doesn't get us there entirely because there's not enough blockchain space for everyone on Earth to have a Lightning channel open. So what you're looking at is going to be a custodial Lightning option, which you all may or may not consider to be a quote L2. Some folks consider an L2 to be a trustless protocol that you can exit unilaterally, which is to say you can exit without asking for anyone's permission. So whether or not you consider custodial Lightning to be L2 or not is up to you. For all intents and purposes, colloquially, I would call that an L2, but please don't hate. So the other option is a Fedimint. And how many of you have heard of eCash? Right? So with eCash, is it custodial? Is it non-custodial? Well, Tony Giorgio, who's also on the Mutiny team, has a pretty cool article saying that Fedimints are non-custodial. So, that's another kind of thought exercise to the audience. So Fedimints are really interesting. David Sham actually created a computer scientist actually created this concept of Shamian eCash, which far predates the concept of Bitcoin itself. And some smart folks have figured out how to apply that technology to Bitcoin. Now, the cool thing about eCash in a fediment, which is a federation, is that unlike Liquid, which is also a federated blockchain, there's no blockchain. And I think, in my opinion, because Liquid is a federation, it doesn't really need a blockchain either. So I think what you're going to see more and more is scaling solutions that don't use blockchains. Imagine that. Now, the fifth option is scaling using blockchains, but creating what are called shared UTXOs or virtual UTXOs. And those are kind of all the rage right now, too. However, they don't exist. So it's a little bit of a problem. And the problem is that in order to get shared UTXOs, we have to soft fork the network. And soft forking the network is actually really hard because in order to do that, we have to form consensus. And the Bitcoin network has actually never defined what that means. There's no definition for what consensus actually is or what the process is by which it's formed, and the process by which we actually create upgrades or soft forks onto Bitcoin is undefined. So, again, a thought exercise to the audience is to ask all y'all, what does consensus mean and how is it found? So I'm going to actually have a really cool conversation with a guy called Reardon later today, and we're going to talk about some of those scaling solution proposals, again, which have not been activated on Bitcoin. His proposal is called L-Enhance, which I think is kind of a little bit of an advertisement for Lightning, right? But what it does also is it enables shared UTXOs, which it remains to be seen if that even is going to be a protocol that we can implement simply enough to even make it work. I mean, what do you guys think?
Yeah, I mean, I think that I think the proposals around covenants are super interesting. So for the audience, just a very quick lowdown of what covenants are and how they might lead to a shared UTXO scheme. Ultimately, the way Bitcoin transactions work, you lock your Bitcoin from some output that was in the UTXO set that's spendable. Then you lock it to another output. You prove that you have the private key with a digital signature. And then it's locked to that address. And then somebody wants to spend from that address, they have to satisfy a set of conditions. It usually should have a digital signature being one of those conditions, but it can also have a hash lock, a time lock, stuff like that. As it currently stands, though, as long as you satisfy those conditions, you can technically send it to anybody. So what covenants do is they basically allow you to constrain your output to a set of outputs they basically need to be matched beforehand, or computed beforehand and then matched at the time of sending. A quick you can imagine with this sort of change to Bitcoin consensus, you can have some different sort of security schemes, right? Even if a hacker gets access to your private key, then there's only a few different addresses you can specify that they can send it to, not necessarily their own. In terms of shared UTXO, this thing actually is a little bit confusing, like this when people say shared UTXO, because I think it doesn't necessarily mean exactly what people think. Like for example, one basic example of a shared UTXO is a Lightning channel. It's a 2 of 2 multisig. It's UTXO, right? There's a 2 of 2 condition, and you're technically sharing it with a channel partner. With covenants, right, and I guess Taproot as well, you can imagine, right, you can basically create a tap tree. So there's like little scripts that you can kind of create of different spending conditions, or just different conditions. You hash them up into this Merkle tree. And with covenants, each of those can go to somebody else, right? Maybe an example, if people are familiar a little bit with quantum computing here, it's like there is a UTXO that's locked to that if there were covenants could spend to a bunch of different exit paths. And if you think in terms of quantum computing, they're all sort of in superposition. So they kind of exist simultaneously at once. It's sharing. You can argue that at some point only one will hit the change. That's kind of what Taproot got us as well. But that maybe helps. And we were talking about shared UTXO being just a very confusing concept.
Yeah, and I think you make a great point. So I like the way you described covenants. So a covenant simply is saying that I'm going to send Bitcoin to you, but you can only send it to Eric, right? Like we're constraining where that Bitcoin can go. But that doesn't actually really scale anything, right? However, there are some proposals for some protocols that use covenants that, to your point, scale Bitcoin, but it remains to be seen. It remains to be seen, for one, it doesn't exist, and two, those protocols haven't actually been fleshed out.
Yeah, it is definitely going to be interesting. I think, just attending BitDevs just provides insight as to the sort of discussions going on, people looking for concrete applications of covenants. Initially there was a lot of talk about the vaults, enhanced security. Then there's people talking about how it can, basically enhance Lightning. Even stuff like BitVM, for example, like using BitVM, which by the way is a relatively new construction, where people cleverly figured out that you can kind of maintain state through different pre-signed Bitcoin scripts or pre-signed transactions.
And that was enabled because of the Taproot soft fork, is that right?
It makes it a lot better. Definitely makes it a lot better and more efficient. But it now allows you to kind of optimistically prove the execution of some function on Bitcoin. So this is again a way that is relatively objectively clunkier than having a fully expressive base layer, but to optimize basically a way to have Turing completeness. If you want, maybe we can go into like two core aspects that people are talking about why BitVM is interesting, or like what BitVM is actually going to be useful for in the near term.
I'd love that.
Yeah.
Yeah, you mentioned Taproot. Taproot did enable BitVM, and I'm just kind of curious for the audience, like how many of you guys are hardware guys? Are there any hardware guys out there? So you guys deal with transistors and logic gates, right? So this is the nerdiest thing you're going to hear all day. Somebody figured, well, Bitcoin script is not fully expressive, it's not Turing complete, but you can build any computer software using logic gates, right? I mean, ultimately that's all that it is on the hardware level. So what if we took those logic gates and put them in the leaves of a freaking tap tree and just built a computer?
Yeah. No, it really is. It really was a brilliant sort of thing to sort of piece together. And if you also pay attention maybe to some of the stuff that Andrew Palestra talks about on Lamport signatures, there's some early properties of Lamport signatures that kind of eventually blended into BitVM. Near term, though, in terms of like what people are useful for, like I've seen demos of people doing like a tic-tac-toe on BitVM. I'm not going to come and necessarily say that's like a useful thing as far as this ecosystem, but maybe it is. Maybe the market will say it is. Who knows? Near term bridging. So as all these layer 2 solutions come up, the different roll-up solutions come up, ultimately without that opcode to verify a zero knowledge proof on Bitcoin, right? We were left with no real options but to have federated multisigs like Liquid. So with BitVM, you technically can have these one of n trust assumption sort of bridges or two-way pegs to rollups. There is some additional discussion on that is a little more nuanced and detailed, but that was part of it. The other part being that because Bitcoin script cannot verify a zero knowledge proof natively right now, that would require opzkp verify. We'd have to agree on a proof system, and then we'd have to commit it into Bitcoin Core eventually. We cannot verify a zero knowledge proof. So even if a rollup came and sent a zero knowledge proof of all the stuff that was happening in the rollup land, the Bitcoin blockchain would not be able to natively understand it and update the UTXO set until some smart people has figured out how to do that at Alpin Labs and others. So there's now a way where you can have BitVM-based snark verification. So you can verify it like a Groth16 snark on Bitcoin with BitVM. Again, more clunky, and that probably will get obsolete if we do eventually get opzkp verify.
I mean, they figured out how to build a computer on Bitcoin. So if you can express it using logic gates, you can express it now on Bitcoin. Now, of course, there are some trade-offs in that this is an optimistic system. So if somebody was to, say, forge or fake the execution of this computer program, you would have to go through a series of transactions to sort of challenge and slash them. And the problem with that is because transactions can sometimes be expensive, as fees get higher, it becomes cost prohibitive to run applications on BitVM that don't really lock up a whole lot of money.
Well, it looks like we only have 5 minutes left for this panel, so maybe, Vikash, if you wanted to talk about some of that machine learning, the report coming out today, I think.
Yeah, it came out today. Yeah.
I'd love to hear it.
Awesome. Yeah, so my background before coming to Bitcoin, as I sort of said before, was a deep learning researcher. So I started doing deep learning research in 2014. Mostly it was deep learning applied to medical imaging. And then I started studying the intersection of deep learning and graphs. So basically how deep learning can be applied to networks to do interesting tasks like link prediction, node classification, all these interesting things. That led me to do deep learning on graphs for quantum computing and deep learning on graphs for biochemistry. And then ultimately when I arrived in Bitcoin, it kind of became very clear that deep learning on graphs for Lightning could be a thing. But that just sounds like a bunch of words, so I'll try to make it kind of meaningful. Lightning, the way that these payments need to work is ultimately you have a source node and a destination node. So you have a set of nodes and you have a set of edges. There's some relationship between all of these entities, right? And we previously discussed these edges being channels, or from Bitcoin blockchain's perspective, 2 of 2 multisig. So we need to have these payments. You need to find a route, right, between source and destination. This is a well-studied problem in the field of computer science. So there are algorithms like Dijkstra's algorithm to find these paths. Ultimately, you define a cost per edge, and you can do that. Ultimately, a researcher, René Pickhardt, kind of, along with the protocol researchers, realized that if you can split these payments up, the proper computer science formulation is as a minimum cost flow problem, another problem where we have methods to solve it. Something unique in Lightning that I think then we kind of go in the machine learning direction is that ultimately the balances of the channels are by default private, right? You don't actually know them. That comes at the cost of maybe having failed payments because in a given direction you might not have enough liquidity. So this recent paper is about sort of modeling those distributions using machine learning. So we take features from the gossip about the channels themselves, right? So these are just properties of the different nodes and the channels. And then from the graph theory perspective, there's a field of math called spectral graph theory that allows us, not just that, there's other adjacent fields that allow us to sort of encode Lightning nodes and channels in higher dimensional spaces. And then we can use this as input to start modeling these distributions. And we sort of show that we can actually do quite a bit better than the default assumptions that are being made in LND and core Lightning. That's what this paper is about. And then you can imagine if you can have a better model of what that distribution is, you plug that into your Dijkstra's algorithm or your min-cost flow solver, and then you get something a little more reliable, right? So that's what this paper is showing. We're going to have a product that's going to be with Amboss technology. It's going to be an API as well. Moving forward, when you look at Lightning rollups and these other things, right? Rollups, for the most part, don't have a payment reliability problem. It's deterministic. You broadcast a transaction, you have the signature, you pay the right fee. Eventually, it should be included in a block, right? There's no uncertainty about things failing. And if we're talking about a payment system reaching anything close to Visa level, SLAs, I don't think, having failed payments is going to be super acceptable, maybe at the most scalable level, right? So that's kind of, what inspired this work. There's a future line of work which we're actively working on, but I'll give you a sneak peek now, which is sort of redesigning Lightning Autopilot from the perspective of simulation, machine learning, and discrete optimization. So this is basically going to help people have an agent that automatically decides what channel to open, who to open to, when to open, and automate that process. If there are any node runners here, I'm sure you guys have experienced the pain of running your own node.
Absolutely. All right. Just a little bit left here, so I really want questions from the audience because while I understood absolutely everything Vikash said, I'm sure other people have questions in the audience. So if you have questions for Vikash or D++, please raise your hand and we'll get a microphone out.
How long do you think any of these innovations will take to occur? Because, optimistic rollups, these are great. They're defined on Ethereum or other chains. Like the notion of getting a ZK opcode, 15 years.
Sure.
30 years optimistically, given the constraints of political consensus in a place where this is not defined.
That's a great question. And when I actually heard that ZK rollups were being built on Bitcoin, I was wondering the same exact thing. Why exactly now? And what are the base layer changes that might need to happen? So I have two answers for you here. One is without BitVM, and one is with BitVM. And we've invested in a zero-knowledge rollup company called Alpen Labs that is developing this. So I've kind of been reading, I've read their white paper in the past and I've studied this. So ultimately, the main constraint is that verification of a zero-knowledge proof on the Bitcoin blockchain, right? That's kind of the constraint. We all agree that's probably not happening anytime super soon. But the question is, does that preclude the development of a zero-knowledge rollup? And there's now several zero-knowledge rollups that are coming to production this year, right? So not in 5 years, like this year. They're working in a few ways. One is you can have an implementation where the zero-knowledge rollup submits the zero-knowledge proof to the Bitcoin blockchain. The Bitcoin blockchain itself does not actually verify the zero-knowledge proof, but you're able to have an implementation where a light client, a separate piece of software that the user interacts with, parses the data from the Bitcoin blockchain. That light client, which you're flexible to design, has the ZK verifier in it, and then it verifies the ZKP, and then ultimately you can reconstruct the entire state of the rollup. So that's one option here, with a trade-off being at the user experience level. The other
Would the miners have to be involved with that, or that could all be?
No, this is no
totally
soft fork needed. Yeah, no soft fork needed. So what you're going to see in this world is a lot of interesting data being posted to the chain that you may not be used to seeing before. These are going to be the ZKPs. You're going to see them on the chain, but they're not going to mean anything really to the chain until the chain gets the upgrade to understand what that means, right? So that's sort of one UX trade-off that's there. The other way is the SNARK-NATO BitVM ZKP verification. So ultimately, there was some cleverness with BitVM, as Dee sort of described, BitVM being able to execute any sort of Turing-complete function on Bitcoin. A zero-knowledge proof verifier is, of course, just another function. So it can be done, and it was done with some clever cryptography tricks too. So there's a BitVM verification of zero-knowledge proof that's going on as well, happening now.
So as a follow-up, VCs have maybe 10-year, thinking out like, okay, we'll cash in in a decade on this bet. But in both scenarios, like we either trust a multi-sig or we're trusting that there will be a political change in the Bitcoin community that's going to allow more arbitrary data to appear. We're already hella triggered by ordinals, inscriptions, and all this other stuff. Like, I love the idea. I think it's wonderful. But there's an ossification guy right next to me. He's actually quite influential in his writings. Like, that's like an iceberg that just seems almost immovable, because people just want number go up.
Yeah, and to be clear, I'm not assuming any of these things are going to happen. I don't assume any of these things are going to happen. But without anything happening today, we can still have some version of a ZK rollup, which we can debate to what degree that's actually a ZK rollup on Bitcoin. It is possible today without any base layer changes.
I've got a question. So with ZK rollups, you have this data availability problem. So where is all this data?
Where is the data? Yeah. So it's interesting. So ultimately, the first answer is that it's going to be living on the Bitcoin blockchain, and the data living on the Bitcoin blockchain allows the zero-knowledge rollup to inherit some aspects of the blockchain sort of immutability, confirmations, and just sort of persistence, right? And if you look at Ethereum land, what they're doing is they're calling these things data availability solutions, things like Celestia. So they're basically creating new data availability layers where people can post the data to those layers. And as you probably guessed, they are not as secure as the L1 chain itself. It cannot be theoretically as secure as the L1 chain itself, but they're posting data there. And ultimately, what this all really comes down to when it comes to fees is what you're paying for. So ultimately, zero-knowledge proof and all these ZK transactions will be paying for some layer 1 block space at the end of the day, and they will be contributing towards Bitcoin consensus if they use Bitcoin as data availability.
Yeah, I guess that's maybe my kind of suspicion of ZKPs, is that you sort of are using blockchains to scale blockchains.
Yeah, it is. So one way of looking at what a zero-knowledge rollup is so we already established that sidechains are a separate blockchain with their own consensus, right? So if you look at Liquid, it has strong federations consensus. You have other sidechains, they can have any BFT consensus, right? A rollup essentially is another blockchain whose state checkpoints into the initial layer 1 blockchain. So there's some relationship between a zero-knowledge layer 2 and the L1 chain where it's inheriting some forms of its security, but definitely not all, right? Because there's still a bridge, there's censorship that can happen on the rollup with the sequencer, all of that sort of stuff. And that's another big thing people talk about with rollups, the fact that there's a central sequencer that needs to be there to batch these transactions, submit them to the chain, order them, right? There's some MEV that occurs, but there's also some censorship that can occur. If that person running that server decides not to send your transactions to the Bitcoin blockchain to confirmation, that's another attack, right? That can happen. There's a lot of talk about shared sequencers in this context. They're like, okay, the thing is, okay, if just one, let's just distribute it. Again, that becomes, in my opinion, another Byzantine fault tolerance problem, where ultimately you may need another chain or some other consensus for that, right? And it may not be open.
Just blockchains all the way down.
Yeah, yeah. So that definitely won't be as open, but it's going to be interesting to see what sort of comes from it.
Hello. So if you're a pleb and you're stacking hard, could you go into some basic ideas? Because when you're sending something on chain and you're acquiring most of your coins KYC, what could you do to reorganize your wallets to be a little bit more anonymous and a little bit more secure, so at the end of the day somebody on the receiving end doesn't see that you're holding a lot of coin, and at least kind of protect yourself when you're in the wild transacting and using Bitcoin and living on a Bitcoin standard?
Yeah, it's a great question. I mean, when it comes to privacy, you have to ask yourself, like, who do you want privacy from? Do you want privacy?
The government.
Well, yeah, so great. So that's important, right? Because if you want privacy from the government, that's sort of a different question than if you want just privacy from the person that you're sending the coins to, type thing. So one of the sticky things about KYC is you can't really ever un-KYC your coin, because if you have bought Bitcoin from an exchange that's KYC'd, even if you put those Bitcoin through different rounds of what's called coin mixing, the government still knows that you have those coins, right? Even if they don't know what your addresses are, or your UTXOs are, they know that this person at one point had this much Bitcoin, and they probably still do. So unfortunately, that can't be undone. So one of the things you can do is you can maintain your KYC stack, and you can create a separate non-KYC stack. And so I, for example, have a separate hardware wallet that I use for my non-KYC coins because I don't want them anywhere near my KYC coins, right? If those coins were to somehow commingle, then it would ruin the anonymity of all of my Bitcoin, right? And we call that toxic change. So there's some trade-offs when it comes to coin mixing. You guys may have heard the news with Samurai. You guys may have heard that they even had everyone's XPubs. I don't know where that list is today. We've had some problems with Wasabi in the past. There are some more kind of decentralized coin mixing platforms like JoinMarket, I think, is probably our best bet as of today if you're looking to coin join. But of course, again, that doesn't un-KYC your Bitcoin, right? It's better just to create a new non-KYC stack.
I heard a couple times the concept of Turing complete. I've heard of like the Turing test. Can you elaborate on what the Turing complete is with you guys were speaking?
Yeah. So that kind of gets into programming language theory a little bit. Maybe the best way to describe Turing complete is that it can kind of compute any function that you can kind of describe, like mathematically. One example here is like Bitcoin script can do some things. There's like op-if, there's like some different like conditions that you can set in Bitcoin script. It does not have loops, right? So more clearly, the stack-based language does not have loops intentionally, whereas a Turing-complete language, any language that you can think of, Python, Java, C++, any of these languages ultimately are Turing-complete in that they can sort of compute any function. So you can map from pseudocode any function that you can dream of, basically, and implement it theoretically in any of these frameworks. Whereas the Bitcoin script is intentionally a lot more limited in its ability to compute these functions.
And with that, looks like we're out of time. So big round of applause for our panel here. Thank you.